Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why alien life might not use DNA, deoxyribonucleic acid, is the molecule of heredity for nearly all life on Earth. From bacteria to blue whales, from mushrooms to sequoia trees, every organism uses DNA to store genetic information, to pass traits from parents to offspring, and to direct the construction of proteins that build and maintain living cells. DNA's structure is elegant and famous, a double helix of two strands twisting around each other, each strand composed of a sugar phosphate backbone with 4 types of bases attached in sequences that encode genetic instructions. DNA seems so fundamental to life that it's easy to assume it must be universal, that any living thing anywhere in the universe would use DNA. But this assumption is almost certainly wrong. DNA is not the only molecule capable of storing and transmitting genetic information, and the specific chemistry that makes DNA work on Earth might not be optimal or even possible under different planetary conditions. To understand why alien life might not use DNA, we first need to understand what DNA actually does and what properties make it suitable for its role. DNA serves 3 critical functions. First, it stores information. The sequence of bases along the DNA strand encodes instructions for building proteins and regulating cellular processes. Second, it replicates. DNA can be copied with reasonable accuracy, allowing genetic information to be passed from one generation to the next. Third, it allows variation. Copying isn't perfect, and occasional errors introduce mutations that create the genetic diversity necessary for evolution. But DNA is not unique in performing these functions. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information, be copied, and undergo evolution despite having different chemical structures than DNA. These molecules use different sugars in their backbones, 3 O's instead of deoxyribose, locked nucleic acids with modified sugars, or even molecules with completely different backbone structures. These XNAs can form base pairs, store sequences of information, and be replicated by specialized enzymes. They demonstrate conclusively that DNA is not the only possible genetic molecule, merely the one that happened to work on Earth. The chemistry of DNA is optimized for Earth's conditions. DNA is stable in liquid water at temperatures roughly between 0 and 40 degrees Celsius, the temperature range where most Earth life operates. The hydrogen bonds holding the 2 strands together are strong enough to keep the double helix intact, but weak enough that the strands can be separated for copying. The sugar phosphate backbone is stable in water at neutral pH, but can be broken down by enzymes when necessary. The bases, adenine, thymine, guanine, and cytosine, are moderately stable molecules that can withstand normal cellular conditions but can be damaged by extreme heat, intense radiation, or strongly acidic or alkaline environments. On a planet with very different conditions, DNA might not function well or at all. Consider a world much hotter than Earth, perhaps a planet orbiting very close to its star, with surface temperatures exceeding 100 degrees Celsius, but with liquid water kept stable by extreme atmospheric pressure. At these elevated temperatures, DNA becomes increasingly unstable. The hydrogen bonds holding the 2 strands together weaken and break more easily. The chemical bonds in the bases and the backbone break down more rapidly. Organisms on such a world would need genetic molecules more heat-resistant than DNA, perhaps with stronger chemical bonds, more stable base structures, or completely different architectures that maintain integrity at high temperatures. Some Earth organisms that thrive in extreme heat have evolved DNA repair mechanisms that constantly fix damage to their genetic material, but there are limits to how hot DNA can tolerate. Beyond a certain temperature, the rate of damage exceeds the capacity of repair mechanisms to fix it. Alien life on a hot world might evolve an alternative genetic molecule with inherently greater thermal stability, perhaps using bases with stronger bonding, or sugars that resist thermal degradation, or entirely different building blocks that remain stable at temperatures where DNA would fall apart within seconds. At the opposite extreme, very cold worlds present different challenges. DNA becomes more rigid at low temperatures, making it harder to separate the strands for copying. The enzymes that copy DNA become less efficient or stop working entirely when too cold. Life on an extremely cold world, perhaps on a moon like Titan, where temperatures hover around -180 degrees Celsius, would need genetic molecules that remain flexible and functional at these frigid temperatures. The chemistry would necessarily be different from DNA, which was shaped by evolution to function in Earth's moderate temperature range. The solvent environment profoundly affects what genetic molecules are possible. DNA functions in liquid water, and its chemical properties are specifically suited to aqueous environments. The sugar phosphate backbone is hydrophilic, attracted to water, which helps keep DNA dissolved in cellular fluids. The bases are hydrophobic, repelled by water, which helps drive base pairing by pushing bases toward each other and away from the surrounding water. This balance creates DNA's structure and stability. In a different solvent, liquid methane, liquid ammonia, or something even more exotic, DNA's chemistry wouldn't work the same way. Water's polarity, its hydrogen bonding capacity, its ability to dissolve certain substances while excluding others. All these properties shape how DNA behaves. In liquid methane, a non-polar solvent, molecules that are hydrophobic in water might become soluble, while hydrophilic molecules might be insoluble. A genetic molecule designed for a methane-based solvent would need completely different chemical properties than DNA, perhaps with non-polar groups exposed to interact with the methane solvent, and polar groups hidden in the molecule's interior. The availability of raw materials constrains what genetic molecules can be built. DNA requires phosphorus, nitrogen, carbon, oxygen, and hydrogen. Phosphorus, though essential for DNA's backbone, is relatively rare in the universe compared to lighter elements. A planet poor in phosphorus might not be able to build DNA-like molecules and would need to evolve genetic systems based on more abundant elements. Perhaps silicon could replace phosphorus in the backbone, or sulfur could play a role, or arsenate, a chemical similar to phosphate, might substitute. Though experiments with arsenate-based DNA on Earth showed it's much less stable than normal DNA. The 4-base system used by DNA, adenine, thymine, guanine, and cytosine, is not the only possible coding scheme. RNA, DNA's chemical cousin, uses uracil instead of thymine, demonstrating that the specific bases aren't fixed. In principle, genetic molecules could use 3 bases, or 6, or even more. More bases would allow more information to be encoded in shorter sequences. With 4 bases, each position in the sequence can encode 2 bits of information, but with 8 bases, each position could encode 3 bits. An alien genetic system might use more or fewer bases depending on what works best with its chemistry. Some scientists have even created expanded genetic alphabets, DNA-like molecules with additional base pairs beyond the natural 4. These synthetic genetic systems can store more information per unit length than natural DNA and can be copied by modified enzymes. The existence of these expanded alphabets demonstrates that the 4-base system is not uniquely optimal, but rather reflects the specific chemistry that evolved on Earth. Alien life might independently evolve genetic systems with different numbers of bases encoding information in different ways. The structure of the genetic molecule might differ radically from DNA's double helix. DNA forms a helix because of how the bases pair and how the sugar-phosphate backbone bends. But other structures are possible. Some XNAs form helices with different geometries, left-handed instead of right-handed, wider or narrower than DNA, with more or fewer base pairs per helical turn. Some synthetic genetic molecules don't form helices at all, but adopt completely different three-dimensional structures. An alien genetic molecule might be a triple helix, a quadruple helix, a ladder without a twist, or some topology we haven't imagined. The copying mechanism might also differ. DNA is copied by enzymes called polymerases that move along the DNA strand, reading the sequence and creating a complementary new strand. This process requires a complex molecular machinery that evolution has refined over billions of years on Earth. Alien life might evolve completely different copying mechanisms, perhaps catalytic RNA-like molecules that copy themselves without protein enzymes, or inorganic crystals that template the formation of complementary structures, or even copying processes that don't involve template-directed synthesis at all, but rather some form of self-assembly guided by the genetic molecule structure. The rate of mutation, how often copying errors occur, affects evolution's pace. DNA polymerases on Earth make errors at a rate of roughly 1 mistake per billion bases, copied for the most accurate enzymes, though rates vary. This error rate is low enough to preserve genetic information across generations, but high enough to generate the variation necessary for evolution. Alien genetic systems might have very different error rates. A system with much lower error rates would evolve more slowly, potentially making adaptation difficult. A system with higher error rates might generate variation faster, but risk genetic information degradation. The optimal error rate depends on generation time, selection pressure, and environmental stability. RNA represents an alternative genetic molecule that exists on Earth and might have preceded DNA in evolution. RNA can store information, catalyze chemical reactions, and replicate all functions DNA cannot perform alone. The RNA world hypothesis proposes that early life used RNA as both genetic material and catalytic molecule before DNA and proteins evolved. An alien world might develop life that remains in an RNA world-like state, never evolving DNA, or might evolve RNA into forms more sophisticated than anything on Earth, creating genetic systems based on elaborate RNA structures rather than DNA. Some scientists have speculated about non-molecular genetic systems. Perhaps information could be stored in the crystal structure of inorganic minerals, with patterns of inclusions, defects, or layering encoding information that could be replicated when crystals grow and form templates for new crystals. Or perhaps information could be stored in magnetic domains in iron-rich minerals, with the orientation of magnetic fields encoding genetic instructions. These ideas are highly speculative and face enormous challenges. How would such systems be read and translated into functional structures? But they illustrate that genetic information storage might not require organic molecules at all. The universality of certain aspects of information storage might transcend specific chemistry. Any genetic system, whether based on DNA, XNA, RNA, or something entirely different, must be able to store discrete, sequential information, symbols arranged in order that can be read and interpreted. This is fundamentally a problem of information theory rather than chemistry. The specific physical substrate that stores the information might be less important than the information itself, and the mechanisms for reading, copying, and translating it into functional structures. If we ever detect alien life, determining its genetic system would be among the first questions we'd want to answer. If alien life uses DNA with the same 4 bases and same genetic code as Earth life, it would suggest either that DNA is universally optimal, unlikely given all the possible alternatives, or that Earth life and alien life share a common origin, perhaps through panspermia. the hypothesis that life can spread between worlds via meteorites or comets. Finding alien life with completely different genetic molecules would confirm that life can independently originate using different chemistry, revealing that DNA is merely one solution among many to the problem of heredity. The genetic code, the mapping between base sequences and amino acids, might also differ. Earth's genetic code is nearly universal across all life, with 3 base sequences called codons specifying which amino acid to insert when building proteins. But the specific assignment of codons to amino acids appears somewhat arbitrary. There's nothing inherent in the chemistry of the codon UUU that demands it code for the amino acid phenylalanine rather than some other amino acid. The code seems to be a frozen accident. Once it was established early in evolution, changing it would be catastrophic because it would alter the meaning of every gene, so it became locked in place. Alien life would likely evolve a completely different genetic code, with different codon assignments, and possibly even a different codon length. 2 base codons, or 4 base codons, or variable length codons. Why alien life might not use DNA comes down to DNA being a solution specific to Earth's conditions: liquid water at moderate temperatures, specific pH ranges, availability of particular elements, and the accidents of chemical evolution that occurred during life's origin on our world. Different conditions would favour different molecules, and even similar conditions might allow evolution to discover different solutions. DNA is remarkable and elegant, but it's not magic or inevitable. It's chemistry, sophisticated, evolved chemistry that works beautifully on Earth, but that represents just one possible answer to the fundamental question of how to store, copy, and transmit genetic information across generations. Across the universe, life might employ countless different genetic systems, each one adapted to its world's unique conditions, each one encoding information and enabling heredity through different molecular mechanisms, proving that while the principle of heredity might be universal wherever life exists, the specific molecular machinery implementing that heredity can vary as widely as the diversity of worlds themselves, with DNA being merely Earth's particular solution to the universal challenge of passing genetic information from parent to offspring through the generations. What alien oceans might contain? Earth's oceans are vast, salty bodies of liquid water covering more than 70% of the planet's surface, containing dissolved minerals, organic molecules, and a staggering diversity of life, from microscopic bacteria to the largest animals that have ever existed. But oceans on other worlds might be fundamentally different, not just in what organisms inhabit them, but in their very composition. What liquids fill them, what chemicals dissolve in those liquids, and what physical conditions prevail at their depths. Understanding what alien oceans might contain means considering not only water-based oceans with different chemistry than Earth's seas, but entirely different liquids that could serve as oceanic solvents on worlds with radically different temperatures, pressures, and geological histories. The most familiar alien oceans would be water-based oceans on other worlds. Several candidates exist in our own solar system. Europa, Jupiter's ice-covered moon, harbours a global ocean containing perhaps twice as much liquid water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's gravity despite surface temperatures around -160 degrees Celsius. This ocean lies beneath an ice shell estimated to be 15 to 25 kilometers thick, shielding the water from the vacuum of space and from Jupiter's intense radiation belts. What Europa's ocean contains remains unknown, but scientific models and the limited data from spacecraft flybys provide clues. The ocean is certainly salty, likely containing dissolved salts leached from Europa's rocky seafloor over billions of years. Magnesium sulfate, sodium chloride, and other salts detected spectroscopically in Europa's ice shell probably came from the ocean below. The salinity might be similar to Earth's oceans, or it might be substantially higher, creating a briny sea where salt concentrations affect water's freezing point, density, and chemistry. High salinity would influence what kinds of life could potentially evolve, favouring organisms with mechanisms to cope with osmotic stress. The ocean would be dark. Absolutely no sunlight penetrates through kilometres of ice. Any life in Europa's ocean would depend on chemical energy rather than photosynthesis. The rocky seafloor might host hydrothermal vents similar to those on Earth's ocean floor, where hot, mineral-rich water spews from cracks in the rock, driven by volcanic heat from the moon's interior. These vents could provide energy and nutrients to support chemosynthetic bacteria that extract energy from chemicals in the vent fluids: hydrogen, methane, hydrogen sulfide, iron compounds. If such microbes exist, they might form the base of a food chain, supporting more complex organisms analogous to the tube worms, clams, and crustaceans that cluster around Earth's hydrothermal vents. Dissolved gases would be present in Europa's ocean: carbon dioxide from reactions between water and rock, hydrogen from water-rock reactions, and possibly from radiolysis, where radiation breaks apart water molecules near the ice-ocean boundary, methane from geological processes, or potentially from biological activity. The concentrations and ratios of these gases would reveal much about the ocean's chemistry and whether biological processes might be occurring. Organic molecules, carbon-based compounds, almost certainly exist in Europa's ocean. Comets and meteorites containing organic compounds have bombarded Europa throughout its history. Chemical reactions between water and rock produce simple organic molecules. If life exists, it would produce far more complex organic molecules: amino acids, lipids, sugars, proteins. Detecting complex organic molecules in samples from Europa's ocean would be strong evidence for biology, though distinguishing biological from non-biological organic chemistry would require careful analysis. Enceladus, Saturn's small moon, provides an even more accessible alien ocean because it actively vents ocean water into space through cracks in its south polar ice shell. The Cassini spacecraft flew through these plumes, analysing their composition directly. The plumes contain water vapour, ice grains, carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic molecules, including some with chains of carbon atoms, ingredients that on Earth would suggest habitability. The presence of molecular hydrogen is particularly intriguing because it suggests water-rock reactions at high temperatures, consistent with hydrothermal vents on Enceladus's seafloor. The organic molecules, while not proof of life, show that organic chemistry is occurring in Enceladus's ocean. Titan, Saturn's largest moon, presents an entirely different type of ocean. Not water, but liquid hydrocarbons. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water, which is frozen as hard as rock. But at these temperatures, methane and ethane exist as liquids. Titan has lakes and seas of liquid hydrocarbons near its poles, bodies of liquid methane and ethane with dissolved propane, butane, nitrogen, and traces of more complex organic molecules. These hydrocarbon seas are hundreds of meters deep in some places, creating environments completely unlike anything on Earth. What Titan's hydrocarbon oceans might contain depends on what chemistry can occur in liquid methane at cryogenic temperatures. Organic chemistry certainly happens. Titan's atmosphere produces complex organic molecules through photochemistry, and these molecules rain down onto the surface, accumulating in the lakes and seas. Nitrogen compounds, cyclic molecules, long-chain hydrocarbons, and possibly even more complex molecules might dissolve in the methane. Whether life could exist in liquid methane remains highly speculative, but if it does, it would use completely different biochemistry than Earth life. perhaps with cell membranes made from molecules that are insoluble in hydrocarbons rather than the water-soluble membranes Earth organisms use. Titan also likely has a subsurface water ocean beneath its icy crust, similar to Europa and Enceladus. This buried ocean would be separate from the surface hydrocarbon seas, creating the possibility that Titan might host two completely different types of chemistry: water-based chemistry in the deep subsurface ocean and hydrocarbon-based chemistry in the surface seas. Whether these two environments could both support life, and whether life in one could be related to life in the other, represents one of the most intriguing questions about this remarkable moon. Ammonia oceans represent another possibility for alien seas. Ammonia remains liquid at temperatures between -77 and -33 degrees Celsius at Earth atmospheric pressure, colder than water but warmer than methane. A planet or moon with temperatures in this range might have oceans of liquid ammonia or ammonia-water mixtures. Pure ammonia is a less effective solvent than water for many compounds, but it can dissolve different substances than water, creating entirely different ocean chemistry. An ammonia ocean would be less dense than water ice, so ammonia ice would sink rather than float, potentially affecting planetary heat transport and ocean circulation. The ocean's pH would be highly alkaline. Ammonia is a base, creating chemistry very different from Earth's near-neutral oceans. Organisms adapted to ammonia oceans would need biochemistry that functions at low temperatures and high pH, potentially using ammonia molecules in ways analogous to how Earth life uses water. Sulfuric acid oceans sound implausible, yet Venus's clouds contain concentrated sulfuric acid droplets, and some scientists have speculated about life existing in these droplets. While Venus's surface is hellishly hot, the cloud layers at altitudes of 50 to 60 kilometers above the surface have temperatures around room temperature, quite comfortable by terrestrial standards. If life could exist as airborne organisms living in cloud droplets, those droplets would be concentrated sulfuric acid, requiring biochemistry completely unlike anything on Earth. Certain Earth microbes can tolerate extremely acidic conditions, proving that acid-resistant biochemistry is possible. But whether life could actually live in sulfuric acid remains unknown and highly controversial. Silicate oceans, molten rock, might exist on lava worlds orbiting extremely close to their stars. At temperatures exceeding 2000 degrees Celsius, rock melts into liquid magma that flows like water. While most scientists consider molten rock too hot and destructive for any conceivable biochemistry, some speculative theories propose exotic life forms based on completely different chemistry that might exist in magma, perhaps using silicate molecules or metal compounds as structural materials instead of carbon-based organic molecules. Such life would be so alien that we might not recognize it as life, even if we observed it directly. Supercritical oceans exist under conditions where temperature and pressure are high enough that the distinction between liquid and gas breaks down. Supercritical water, existing at temperatures above 374 degrees Celsius and pressures above 220 atmospheres, has properties intermediate between liquid and gas. Deep beneath the surfaces of massive ocean worlds, pressures might be high enough to create supercritical water oceans. The chemistry in supercritical water differs dramatically from normal water chemistry, with different solubilities, reaction rates, and molecular interactions. Whether life could adapt to supercritical conditions remains unknown, but the possibility can't be ruled out for extremely exotic organisms. The ocean floor composition profoundly affects ocean chemistry. Earth's ocean floors are basaltic rock, and water-rock interactions continuously cycle elements between the ocean and the crust. Alien ocean floors might be different, perhaps pure ice if the ocean is deep enough that high-pressure ice forms at the bottom, or perhaps carbonate rocks, serpentinite, or other minerals depending on the planet's composition. These different minerals would leach different elements into the ocean, creating different dissolved chemistry. Hydrothermal vents on alien seafloors might vent fluids with very different composition than Earth's vents. On Europa or Enceladus, where the rocky interiors might be rich in different minerals than Earth's mantle, vent fluids might contain unusual concentrations of metals, sulfur compounds, or other chemicals. These different chemistries would favour different types of chemosynthetic organisms if life exists, potentially creating ecosystems with no analogue on Earth. Dissolved oxygen would be rare or absent in most alien oceans unless photosynthetic life has evolved and produced oxygen for billions of years as on Earth. Most alien oceans would be anoxic, without dissolved oxygen, more similar to Earth's oceans before the Great Oxidation Event 2.5 billion years ago. Anoxic oceans contain different dissolved metals and have different chemistry than oxygenated oceans. Iron remains dissolved in anoxic water instead of precipitating as rust. Sulfur chemistry dominates, rather than oxygen chemistry. Life in anoxic alien oceans would use anaerobic metabolism, extracting energy from reactions that don't involve oxygen. Temperature gradients in alien oceans depend on heat sources. Earth's oceans are heated from above by sunlight and from below by geothermal heat, creating complex circulation patterns. Europa's ocean, heated only from below by tidal heating and with a cold ice ceiling above, might have upside-down circulation compared to Earth. Warm water rising from the seafloor toward the ice ceiling where it cools and sinks back down. These circulation patterns would affect nutrient distribution, temperature zones, and where life might be most abundant. Pressure increases with depth in any ocean, but the rate depends on the liquid's density and the world's gravity. Europa's ocean might reach pressures exceeding 10,000 atmospheres at the seafloor, much higher than Earth's deepest ocean trenches due to the ocean's great depth. Organisms adapted to such extreme pressure would have specialized biochemistry that functions under conditions where molecules are compressed and reaction rates are altered by pressure's effects on molecular structure. Seasonal variations might affect some alien oceans. A planet with significant axial tilt would experience seasonal changes in star heating that could affect surface ocean temperatures, causing seasonal mixing, ice formation and melting, and biological cycles tied to seasons. Tidally locked planets would have no seasonal variations, but might have temperature zones related to distance from the substellar point, the location where the star is directly overhead, creating warm equatorial regions and cold polar regions with different ocean chemistry in each zone. Ice-covered oceans might have ecosystems concentrated near the ice-water boundary, where any photosynthesis using radiation penetrating through cracks in the ice could occur, or where chemical gradients between the ice and deep ocean creates energy harvesting opportunities. Life might cluster in cracks and crevices in the ice ceiling, or in regions where the ice is thinnest and most likely to crack or melt. What alien oceans might contain ranges from the familiar, salty water with dissolved minerals and potentially abundant life, to the exotic, liquid methane seas with dissolved organic compounds, ammonia oceans at cryogenic temperatures, supercritical fluids blurring the line between liquid and gas, even molten silicate magmas on scorching hot worlds. Each ocean's composition reflects its world's temperature, pressure, geology, and history, creating environments where chemistry operates under different rules, where life, if it exists, would be adapted to conditions we can barely imagine, where exploration by future spacecraft might reveal ecosystems as diverse and wondrous as Earth's oceans, or so alien that we struggle to recognize biology when we see it, expanding the inventory of habitable environments to include not just Earth-like water oceans, but any stable liquid where dissolved chemicals, energy sources, and sufficient time might allow chemistry to evolve into biology beneath the waves of alien seas scattered across the solar system and beyond. What intelligent alien technology might reveal. The search for extraterrestrial intelligence has focused primarily on listening for radio signals, deliberate transmissions from alien civilizations trying to communicate across the cosmos. Since 1960, when astronomer Frank Drake conducted the first systematic search for alien radio signals in what came to be called Project Ozma, scientists have scanned the sky with increasingly sensitive radio telescopes, hoping to detect patterns in the cosmic static that would indicate intelligent origin. But radio signals represent just one possible technological signature among countless ways that advanced civilizations might make their presence known across interstellar distances. Understanding what intelligent alien technology might reveal means thinking beyond communication attempts to consider the inevitable side effects and engineering projects that any sufficiently advanced civilization would produce. Technology leaves traces. Human civilization has only been producing radio signals for about a century. Yet already, our technological fingerprint extends outward in a sphere over 200 light-years in diameter, expanding at the speed of light. Television broadcasts, radar installations, radio communications, all of this electromagnetic radiation leaks into space, creating a bubble of human-generated signals spreading through the galaxy. An alien civilization with sensitive enough radio telescopes could detect these signals and know that an industrial, technological species exists on Earth, even if we never intentionally try to contact them. Our technology reveals us whether we choose to advertise our presence or not. The same principle applies to alien civilizations. Any technological species using electromagnetic radiation for communication, navigation, or industrial processes would inadvertently create detectable signals. The frequency, pattern, and characteristics of these signals would differ from natural astronomical sources. Natural radio emissions from stars, nebulae, and other cosmic objects tend to be broadband, spread across a wide range of frequencies, or if narrowband, they're produced by specific atomic or molecular transitions at predictable frequencies. Artificial signals, in contrast, might be extremely narrowband, might drift in frequency in patterns that reflect the relative motion of transmitter and receiver, or might contain modulations and patterns that have no natural explanation. The famous WOW signal detected in 1977 by the Big Ear radio telescope at Ohio State University demonstrated what a potential technosignature might look like. For 72 seconds, the telescope received a strong, narrow-band signal from the direction of the constellation Sagittarius. The signal was so unusual that astronomer Jerry Amon wrote "Wow" on the printout, giving the detection its name. The signal has never been detected again, despite decades of subsequent observations, and its origin remains unexplained. It might have been terrestrial interference, or a reflection off space debris, or a natural phenomenon we don't yet understand, or it might have been exactly what it appeared to be, a brief, powerful transmission from an alien source that was never repeated. Optical signals represent another detection method. Laser technology on Earth has advanced to the point where powerful lasers could, in principle, outshine the sun at specific wavelengths for brief moments. If we pointed a sufficiently powerful laser at a star, an alien astronomer observing from that star system might detect the flash, recognizing it as artificial because of its extreme brightness at a single wavelength. This is the basis for optical SETI, the search for brief, intense laser pulses from other civilizations. Aliens might use lasers for interstellar communication because lasers are highly directional and can carry large amounts of information. A civilization intentionally trying to contact other species might beam powerful laser pulses toward nearby stars, hoping someone is watching. But some of the most compelling technosignatures might come not from communication attempts, but from large-scale engineering projects. Any advanced civilization would need energy, and energy requirements grow as civilizations become more technologically sophisticated. In 1964, physicist Freeman Dyson proposed that a sufficiently advanced civilization might construct a vast structure around its star to capture a significant fraction of the star's total energy output. This structure, called a Dyson sphere or Dyson swarm, might consist of countless solar panels, habitats, or other components orbiting the star, intercepting sunlight and converting it to useful energy. A complete Dyson sphere would make the star invisible at visible wavelengths. All the light would be absorbed by the structure, but the structure would glow in infrared radiation, emitting the waste heat from whatever processes the captured energy powered. From a distance, a star surrounded by a Dyson sphere would appear anomalously bright in infrared, while being dim or invisible in visible light. Astronomers have searched for such infrared excess stars, cataloguing objects that might be Dyson spheres. Though all candidates discovered so far have more mundane explanations like dust clouds or unusual stellar properties. Megastructures don't need to enclose entire stars to be detectable. A single, enormous structure in orbit around a star might block a tiny fraction of the star's light as it passes in front of the star from our perspective. This would create a transit, a dip in the star's brightness, similar to what happens when a planet transits its star. But while planetary transits follow regular, predictable patterns with consistent depths and durations, a megastructure might create irregular, asymmetric transits that don't match any natural explanation. The star KIC 84462852, also known as Tabby's star after astronomer Tabitha Boyajian, who led the research team that discovered its unusual behaviour, demonstrated what such anomalies might look like. This star, observed by the Kepler Space Telescope, exhibited irregular, dramatic dips in brightness, sometimes dropping by more than 20%, that didn't match the patterns expected from planets, dust clouds, or any other standard astronomical explanation. The irregular timing and unusual shapes of the dimming events led some researchers to speculate about megastructures, though most scientists now favour natural explanations involving dust and debris, possibly from a disintegrating comet or planet. Still, Tabby's star showed that we could detect anomalous dimming patterns, and if megastructures exist, similar observations might reveal them. Atmospheric pollution represents a more subtle, but potentially detectable, technosignature. Industrial civilizations inevitably alter their planet's atmosphere through their activities. On Earth, the Industrial Revolution increased carbon dioxide levels, added artificial chemicals like chlorofluorocarbons, and changed atmospheric chemistry in detectable ways. Some proposed technosignatures involve looking for molecules in exoplanet atmospheres that shouldn't exist naturally. Chlorofluorocarbons, for instance, are entirely artificial. They don't form through natural processes, but are produced industrially. Detecting CFCs in an exoplanet's atmosphere would be strong evidence for industrial activity. Similarly, nitrogen dioxide concentrations above natural levels could indicate industrial combustion. Certain combinations of atmospheric gases might indicate technological activity. For example, large amounts of both oxygen and methane in the same atmosphere shouldn't coexist naturally because these gases react with each other. If both are abundant, something must be continuously producing them. While biology can produce both gases, certain ratios or the presence of specific isotopes might point toward industrial rather than biological sources. City lights offer another potential technosignature. Earth's night side is dramatically brighter than it was before artificial lighting, with cities visible from space as brilliant concentrations of light. An alien civilization observing Earth with sufficiently powerful telescopes could detect this artificial illumination, recognizing it as technological in origin because the light spectrum differs from natural phenomena like forest fires or volcanic activity. The light would also be concentrated in specific patterns, along coastlines, in networks of roads, around population centers, rather than being randomly distributed. Detecting city lights on exoplanets would be extraordinarily challenging with current technology. The light from the planet's star overwhelms the faint glow of artificial lighting by enormous margins. But future telescopes, particularly those designed to directly image exoplanets by blocking the star's light, might have the sensitivity to detect bright illumination on a planet's night side, especially if the civilization uses inefficient lighting that wastes energy as light escaping into space, rather than being directed downward toward the ground. Space-based infrastructure might be detectable through reflected light or occultations. Satellites, space stations, solar panel arrays, and other orbital structures reflect light from their star. A civilization with extensive orbital infrastructure might create a faint cloud of reflected light around their planet, detectable as excess brightness beyond what the planet itself would reflect. Similarly, large orbital structures might occasionally pass in front of stars in the background as seen from Earth, creating very brief, tiny dips in brightness that could be detected through careful monitoring. Propulsion systems represent another potential technosignature. Any civilization attempting interstellar travel would need enormous energy to accelerate spacecraft to significant fractions of light speed. Some proposed propulsion systems would create detectable signatures. Nuclear pulse propulsion, using nuclear explosions for thrust, as proposed in the Orion project, would create distinctive radiation signatures. Antimatter engines would produce gamma rays from matter-antimatter annihilation. Fusion drives would create specific spectral signatures from the fusion reactions. Even laser-pushed light sails, sails accelerated by powerful lasers from the home star system, would create bright laser beams visible across interstellar distances to anyone positioned along the beam's path. Gravitational engineering, if possible, might create detectable anomalies. If advanced civilizations can manipulate gravity or space-time, something beyond our current technological capabilities, but not necessarily forbidden by physics, their activities might create detectable effects. Artificial gravitational waves at unusual frequencies, anomalous motions of stars or planets that suggest artificial manipulation, or regions of space with unexplained gravitational properties could all potentially indicate advanced technology at work. Asteroid mining and large-scale resource extraction would alter the appearance of solar systems. A civilization mining asteroids for raw materials would change the distribution and size of asteroids over time. Spectroscopic observations might reveal unusual compositions in asteroid belts, perhaps unusually low concentrations of useful metals if those metals have been extensively mined. Debris from mining operations might create distinctive dust clouds with unusual properties. Stellar engineering represents the extreme end of technological signatures. Some theorists have proposed that advanced civilizations might manipulate stars themselves, extracting material from stars, changing stellar composition, or even moving stars through space using enormous thrusters. These Shkadov thrusters, named after physicist Leonid Shkadov, would use mirrors or other structures to create thrust from a star's own radiation pressure, allowing the star to be slowly moved over millions of years. A civilization might move their star to escape dangers like nearby supernovae, to position their star system optimally in the galaxy, or to transport their entire solar system on an interstellar journey. A moving star whose motion couldn't be explained by gravitational interactions with other objects might indicate such stellar engineering. Time also factors into detectability. A civilization's technological signatures change as technology evolves. Humanity's radio era might be brief, perhaps only a few centuries between when we developed radio technology and when we transitioned to communication methods that don't leak into space, like fiber optics or directed transmissions. An alien civilization might have a similarly brief radio-loud period. This means that civilizations at different technological stages would produce different signatures. An early industrial civilization might produce atmospheric pollution, but no radio signals. A spacefaring civilization might have extensive orbital infrastructure, but might no longer use radio for communication. An extremely advanced civilization might produce signatures we cannot yet imagine, using technologies and engineering approaches completely beyond our current conceptual framework. The absence of detected technosignatures, despite decades of searching, has led to discussions of the Fermi paradox. If technological civilizations are common, where are their signatures? Perhaps they're too rare or too distant. Perhaps they exist but avoid broadcasting or producing detectable signatures intentionally. Perhaps our detection methods are inadequate or focused on the wrong signatures. Or perhaps advanced civilizations develop technologies that produce no detectable signatures, or signatures we wouldn't recognize because we're not looking for them. What intelligent alien technology might reveal encompasses everything from deliberate messages transmitted across space to the inevitable waste heat and pollution from industrial processes, from the dimming of stars caused by megastructures to the reflected light from orbital infrastructure, from laser flashes used for communication to the gravitational anomalies created by stellar engineering. Each technological signature represents a different window into how civilizations develop, what they value, what problems they solve, and how they reshape their environments. Detecting any of these signatures would answer one of humanity's deepest questions: are we alone? And would provide our first glimpse into how other intelligences have developed technology, overcome challenges, and left their mark on the cosmos, transforming our understanding of what's possible, and revealing that the universe contains not just stars, planets, and lifeless matter, but minds that contemplate the cosmos just as we do, minds that build and create and reach toward the stars. What alien civilizations might actually look like? When most people imagine alien civilizations, they picture humanoid beings with large heads, sleonder bodies, and advanced technology that allows them to cross the vast distances between stars. Science fiction has given us countless variations: green-skinned Martians, insectoid hive minds, crystalline energy beings, peaceful explorers, and hostile invaders alike. But what would alien civilizations actually look like if we base our expectations on biology, physics, chemistry, and evolutionary principles rather than imagination alone? The answer reveals possibilities both familiar and utterly strange, shaped by the same fundamental laws that govern life on Earth, but expressed through the infinite variations that different worlds and evolutionary histories would create. The foundation of any alien civilization begins with evolution. On Earth, every organism exists because its ancestors survived and reproduced more successfully than competitors. Natural selection shaped everything from bacterial flagella to human brains, optimizing organisms for their specific environments and challenges. The same process would operate on any world where life exists. Alien organisms would be shaped by their planet's gravity, atmosphere, temperature, available nutrients, predators, and countless other factors operating over millions or billions of years. Evolution is relentless, creative, and opportunistic, finding solutions to survival challenges through whatever mechanisms work. Gravity would profoundly influence alien body structures. On a high-gravity planet, perhaps 1.5 times Earth's gravity, organisms would need stronger skeletal structures to support their weight. Animals might evolve shorter, stockier bodies with thicker bones and more powerful muscles. Tall, slender forms would be disadvantageous because they would require too much structural support and energy to maintain. Intelligent beings on such a world might stand only 3 or 4 feet tall despite being as massive as humans, with powerful legs and low centers of gravity to move efficiently under the stronger gravitational pull. On a low-gravity planet, the opposite constraints would apply. With less gravitational force to overcome, organisms could grow taller and more delicate. Bones could be lighter and more slender. Flying might be easier, allowing evolution to produce larger flying organisms than Earth's giant pterosaurs. Intelligent beings might stand 8 or 10 feet tall with elongated limbs, moving with a grace that would seem almost balletic to Earth-based observers. Their skeletal structure might resemble bird bones, hollow and reinforced with internal struts rather than solid like mammalian bones. The atmospheric composition would shape how aliens breathe and what biochemistry they use. On Earth, most complex life uses oxygen for metabolism because burning fuel with oxygen releases large amounts of energy efficiently. But oxygen was not always abundant. Early Earth had an atmosphere dominated by nitrogen, carbon dioxide, methane, and other gases. The oxygen we breathe today came from photosynthetic bacteria that gradually transformed the atmosphere over billions of years in what's called the Great Oxidation Event. An alien planet might never undergo such a transformation, leaving its atmosphere oxygen poor. Life there might use different metabolic pathways, perhaps based on sulfur compounds, hydrogen, or methane. The type of star a planet orbits would influence alien vision and perhaps their entire sensory experience of reality. Our sun emits most strongly in visible light wavelengths, the colors we can see, and Earth's organisms evolved eyes sensitive to these wavelengths because that's where the most light was available. But a planet orbiting a red dwarf star would receive most of its light in infrared wavelengths. Organisms evolving there might develop eyes sensitive to infrared rather than visible light. To them, what we call visible light might be invisible ultraviolet, and their daylight would be our infrared. An alien from such a world would perceive colors and see objects in ways completely foreign to human experience. Conversely, a planet orbiting a hotter, bluer star would receive more ultraviolet light. Evolution might produce eyes sensitive to ultraviolet wavelengths, allowing these aliens to see patterns and colors invisible to humans. Many Earth organisms, including bees and some birds, can already see into the ultraviolet range, perceiving patterns on flowers and plumage that humans cannot detect without special cameras. An alien species with full ultraviolet vision would experience a visual world enriched with information and beauty we cannot access. Communication methods would evolve based on environmental constraints and available sensory channels. On Earth, humans primarily communicate through sound, speaking and hearing, supplemented by visual cues like facial expressions and gestures. But sound travels poorly in thin atmospheres and not at all in vacuum. An alien species on a world with a thin atmosphere might rely more heavily on visual communication, color changes, bioluminescent patterns, or elaborate gestural languages. Octopuses on Earth already use color-changing skin cells, called chromatophores, to communicate, creating flowing patterns across their bodies. An intelligent species with similar abilities might communicate through rapidly shifting color displays, conveying complex ideas through patterns that flow across their skin in what would appear to us as living art. Some aliens might communicate through vibrations transmitted through the ground or through their planet's oceans. Whales and elephants on Earth use low-frequency sounds that travel great distances. Elephant calls can travel several miles through the ground. An intelligent species might evolve specialized organs for creating and detecting vibrations, communicating through seismic signals that travel through rock or sediment. Their language would be invisible and inaudible to humans without special equipment to detect the vibrations. Chemical communication, already used extensively by Earth's insects through pheromones, might become the primary communication method for some species. Aliens might communicate through releasing complex mixtures of chemicals that other members of their species detect through sensitive chemoreceptors. Their language would consist of scents and tastes, with grammar and syntax encoded in the ratios and combinations of different molecules. To humans, their most profound poetry and scientific papers would be nothing more than smells. Body structure would reflect evolutionary history and environmental pressures. The bilateral symmetry seen in most Earth animals, a left side mirroring a right side, emerged early in evolution and became locked in. But aliens might evolve radial symmetry, like starfish, with body parts arranged around a central axis. An intelligent being with radial symmetry might have arms, eyes, and sensory organs distributed evenly around their body, giving them a 360-degree field of awareness with no natural front or back. Their psychology and culture might be profoundly affected by experiencing the world without a preferred direction of travel or attention. The number of limbs is not fixed by any physical law. Earth's vertebrates settled on 4 limbs relatively early in evolutionary history, but arthropods, insects, spiders, crustaceans have 6, 8, or even dozens of legs. An alien species might evolve with 3 limbs arranged in a triangle, giving them stable tripod support at all times. They might have 6 limbs, 4 for walking and 2 manipulator arms. Or they might have dozens of tentacles like an octopus, each capable of independent complex movement and manipulation. Their tool use and technology would develop along entirely different lines than human technology, shaped by their different manipulative abilities. Intelligence itself might manifest in forms unlike human intelligence. Human intelligence is highly centralized. Most of our cognitive processing occurs in our brain, a single organ in our head. But octopuses, among Earth's most intelligent invertebrates, have a distributed nervous system with neurons throughout their arms that can make independent decisions. An alien species might have multiple brain centers distributed throughout their body, or they might have a collective intelligence where individual organisms are relatively simple, but groups display emergent intelligence through their interactions, similar to how ant colonies solve complex problems that individual ants cannot. Social structure would influence civilization development. Humans are intensely social primates who naturally form groups, cooperate, compete, and create complex hierarchies. An intelligent species that evolved from solitary predators might have very different social instincts, perhaps coming together only to mate and raise young, then separating again. Their civilization would be built by individuals who value isolation and independence over community and cooperation. Or aliens might be eusocial, like bees or ants, with specialized castes, workers, soldiers, reproducers, genetically programmed for different roles. Their civilization might function as a superorganism where individual identity barely exists. Lifespan would profoundly affect culture and technology development. If an alien species naturally lives for thousands of years, they might approach problems with a patience humans cannot fathom, willing to spend centuries on single projects. Their sense of urgency and change would operate on timescales that would frustrate any human trying to interact with them. Conversely, a species with lifespans of only a few years might compress their entire cultural and technological development into periods that humans would find incomprehensibly rapid. Environmental factors would shape not just biology, but psychology and culture. A species that evolved in oceans might think about space and boundaries very differently than land-dwelling humans. Without solid ground beneath them, without permanent structures that last for generations, their concepts of property, territory, and permanence might be fluid in ways humans struggle to understand. A species that evolved in dense forests with limited sightlines might have very different concepts of distance and perspective than humans who evolved in open savannas, where seeing for miles was possible and valuable. Technology would develop based on available resources and environmental challenges. A civilization on a water world with no dry land would never discover fire, fundamentally altering their technological development pathway. Without fire, they couldn't easily work metals, make pottery, or develop steam power. Their technology might focus on biological engineering, breeding organisms to serve specific functions, or on working with materials that don't require heat processing. They might develop advanced understanding of hydrodynamics, pressure, and acoustic phenomena, while lacking technologies that humans developed early. A civilization on a planet with extreme temperature swings might prioritize insulation and environmental control. A species on a tidally locked planet with one side in permanent daylight and the other in eternal darkness might build their civilization in the twilight zone between extremes. Or they might develop two separate cultures adapted to the radically different environments. Their technology would need to handle these extremes, perhaps leading to advanced materials science long before other fields developed. Reproduction methods would influence family structures and social organization. If aliens reproduce through spawning like fish, releasing eggs and sperm into water where fertilization occurs externally, they might have no concept of nuclear family or parental bonds. Eggs might be raised communally or even left to develop independently. If reproduction requires 3 or more sexes simultaneously, their social structures and mating rituals would be incomprehensibly complex to humans. If they reproduce through budding or fission, creating genetic copies of themselves, their concepts of individuality and identity might be fundamentally different from species that reproduce sexually and value genetic diversity. Sensory experiences beyond human comprehension might exist. Some Earth organisms detect magnetic fields, electric fields, pressure changes, or polarized light, senses humans lack entirely. An alien species might perceive reality through senses we don't possess and cannot easily imagine. They might see the world through echolocation like bats, building a sonic map of their environment. They might sense electrical fields like sharks detecting the bioelectric signatures of other organisms. They might perceive time differently, with reaction times much faster or slower than humans, making their subjective experience of duration incompatible with ours. The Fermi paradox asks why, if alien civilizations are likely to exist, we haven't detected them yet. One possible answer is that we're looking for the wrong things. We search for radio signals because that's how we communicate, and we look for visible structures, like cities, because that's how we build. But an alien civilization might never develop radio technology, using entirely different communication methods. They might build in ways that leave no visible trace from space. They might exist on entirely different timescales, civilizations that rise and fall in centuries, while humans are still learning to farm, or civilizations that operate so slowly that their entire recorded history spans less time than a human lifetime. If contact ever occurs between human and alien civilizations, the challenges would be immense. Even if both species are trying to communicate, fundamental differences in sensory experience, cognition, timescales, and conceptual frameworks might make mutual understanding nearly impossible. Imagine trying to explain color to someone born blind, or music to someone born deaf, or love to a species that doesn't experience emotions. Now multiply those challenges by every aspect of existence: time, space, causation, identity, purpose. Communication might require generations of effort and specialized translation technologies we haven't yet imagined. What alien civilizations might actually look like encompasses possibilities ranging from vaguely familiar, carbon-based organisms breathing oxygen on Earth-like worlds shaped by convergent evolution into forms somewhat similar to Earth's creatures, to utterly incomprehensible beings whose very existence challenges our definitions of life, intelligence, and civilization. They might be silicon-based entities living in molten rock at temperatures that would vaporize Earth's organisms. They might be electromagnetic patterns in planetary magnetic fields, or chemical reaction networks in liquid methane seas, or quantum coherence patterns in neutron star crusts. The universe is vast and ancient, and if intelligence has emerged elsewhere, it has had billions of years and countless different environments in which to develop into forms limited only by physics, chemistry, and the creative power of evolution operating across deep time on worlds we've never seen. What's left after a star explodes? When a massive star reaches the end of its life and explodes in a supernova, the detonation is one of the most violent events in the universe, releasing in a few seconds as much energy as the sun will radiate over its entire 10 billion year lifetime. The outer layers of the star are blasted into space at thousands of kilometers per second, creating an expanding shell of hot gas enriched with newly forged elements. But the explosion doesn't simply obliterate the star. At the center of the expanding debris, something remains, a compact, incredibly dense object created from the collapsed core. What gets left behind depends on the mass of that core and determines whether the remnant becomes a neutron star, a pulsar, a magnetar, a black hole, or in rare cases, nothing at all. The immediate aftermath of a core collapse supernova leaves behind a proto-neutron star, an extremely hot, dense ball of neutrons about 20 to 30 kilometers in diameter, containing between 1.4 and about 3 solar masses compressed into a volume smaller than a city. The temperature at birth exceeds 100 billion degrees Celsius, making it one of the hottest objects in the universe. Over the next 10 to 20 seconds, the proto-neutron star cools by emitting enormous numbers of neutrinos, ghostly particles that barely interact with matter but carry away 99% of the supernova's energy. As the proto-neutron star cools and stabilizes over minutes to days, it becomes a neutron star, a stellar remnant held up against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons being compressed too closely together. The density is extraordinary, about 500 million tons per cubic centimeter, comparable to compressing all of humanity into a volume the size of a sugar cube. A neutron star is essentially a single gigantic atomic nucleus, held together by gravity rather than the strong nuclear force. The structure of a neutron star is layered and complex. At the surface lies a thin atmosphere, only centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, about a kilometer thick, where matter exists as a crystalline lattice of atomic nuclei, extremely neutron-rich nuclei unlike any found on Earth, embedded in a sea of electrons. These nuclei become increasingly neutron-rich with depth, containing far more neutrons than protons. Deeper still, at the interface between outer and inner crust, neutrons begin to drip out of nuclei, creating a neutron superfluid that coexists with the nuclear lattice. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever, a quantum mechanical phenomenon that can only occur at extremely low temperatures or extremely high densities. In neutron stars, despite the enormous temperatures by human standards, the density is so extreme that superfluidity occurs. The inner crust, extending to about 10 kilometers depth, consists of increasingly exotic arrangements of nuclei and superfluid neutrons. Computer simulations predict that nuclei might arrange into cylindrical rods, flat plates, or even more complex three-dimensional structures nicknamed nuclear pasta because of their resemblance to spaghetti, lasagna, and other pasta shapes. This nuclear pasta might be the strongest material in the universe, billions of times stronger than steel. Below the crust lies the outer core, where nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain electrical neutrality. Both the neutrons and protons exist in superfluid and superconducting states respectively. The protons form a superconductor, where electrical currents can flow without resistance. This region makes up the bulk of the neutron star's mass and extends to perhaps 10 to 12 kilometers from the center. At the very center, in the inner core, where densities exceed that of atomic nuclei by factors of 2 to 10, matter might exist in states never observed in laboratories. Neutrons themselves might break down into their constituent quarks, creating quark matter or strange quark matter. Other exotic particles predicted by quantum chromodynamics, the theory describing the strong nuclear force, might appear, including hyperons, kaons, or pion condensates. The exact nature of matter at these densities remains one of the great unsolved problems in physics, accessible only through observations of neutron stars and theoretical calculations. Many neutron stars are born rotating rapidly, spinning tens or hundreds of times per second, inheriting and concentrating the angular momentum of the massive star's core as it collapsed. If the neutron star's magnetic field is tilted relative to its rotation axis, which is common, the neutron star becomes a pulsar. The magnetic field, enormously compressed and amplified during the collapse, can reach strengths of 1 trillion times. Earth's magnetic field. Charged particles accelerated along magnetic field lines near the poles emit beams of radiation that sweep through space like a cosmic lighthouse. When one of these beams sweeps across Earth, we detect a pulse, hence the name pulsar. The pulses arrive with extraordinary regularity. The Crab pulsar, formed in the supernova observed in 1054 AD, rotates 30 times per second. The fastest pulsar known, PSRJ 1748-2446 AD, discovered in 2006, rotates 716 times per second, so fast that its equator is moving at about 24% of the speed of light. At these rotation rates, the neutron star bulges significantly at its equator but holds together through its tremendous gravitational binding and the strength of neutron-degenerate matter. Pulsars gradually slow down over millions of years as their magnetic fields radiate energy and carry away angular momentum. The rate of slowdown reveals the pulsar's age and magnetic field strength. Young pulsars like the Crab slow down noticeably over human timescales. The Crab's rotation period increases by about 38 nanoseconds per day. Old pulsars slow down much more gradually and eventually become too slow to generate detectable pulses, though the neutron star continues existing as a dark, cooling ember. Some neutron stars are born with even stronger magnetic fields, up to 1,000 times more intense than typical pulsars, reaching magnetic field strengths of 10 to the 15th Gauss. These objects are called magnetars, and they're the strongest magnets in the universe. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms become elongated into needle-like shapes. The magnetic field stores so much energy that magnetars occasionally undergo starquakes, sudden rearrangements of the neutron star's crust that release tremendous bursts of X-rays and gamma rays. The magnetar SGR 1806-20 released a giant flare in 2004 that briefly saturated instruments across the solar system despite being 50,000 light-years away. Not all neutron stars become pulsars. If the magnetic field happens to be nearly aligned with the rotation axis, the beams don't sweep across our line of sight, and we don't see pulses. These objects, often called radio-quiet neutron stars, or simply isolated neutron stars, are much harder to detect. They can only be found through their thermal emission. They're hot enough, at temperatures of a few million degrees to emit X-rays. The Hubble Space Telescope and X-ray observatories have identified several dozen of these isolated neutron stars, though many more certainly exist undetected. Binary systems where a neutron star has a companion star create unique situations. If the companion is a normal star and the orbit is close enough, the neutron star's gravity can pull material from the companion. This material spirals inward through an accretion disk, heating to millions of degrees and emitting intense X-rays before crashing onto the neutron star's surface. These X-ray binaries can be incredibly luminous, sometimes outshining entire galaxies in X-rays. The infalling material also carries angular momentum, spinning up the neutron star. Over millions of years, an old, slow-spinning pulsar can be recycled into a millisecond pulsar, rotating hundreds of times per second, rejuvenated by mass transfer from its companion. When two neutron stars orbit each other, they form a binary neutron star system. Objects like the Hulse-Taylor binary, discovered by Russell Hulse and Joseph Taylor in 1974, which earned them the 1993 Nobel Prize in Physics. These systems emit gravitational waves, ripples in spacetime that carry away orbital energy. As they lose energy, the neutron stars spiral closer together. Eventually, after millions or billions of years, they merge in a catastrophic collision. The merger produces intense gravitational waves, events that LIGO and other gravitational wave observatories have detected, along with a kilonova, a spectacular explosion that creates heavy elements like gold and platinum through rapid neutron capture. The merger of two neutron stars can produce different outcomes depending on the total mass. If the combined mass is below about 2.2 to 2.9 solar masses, the exact threshold remains uncertain. The merger might create a more massive neutron star, though one that's likely unstable and will soon collapse. If the total mass exceeds this threshold, the merger immediately creates a black hole, with no stable neutron star phase at all. The LIGO detection in 2017, designated GW170817, appears to have created either a hypermassive neutron star that collapsed within seconds or a black hole directly. If the collapsing core of a supernova exceeds about 2.2 to 3 solar masses, again, the exact threshold depends on the poorly known equation of state of nuclear matter. Neutron degeneracy pressure cannot halt the collapse. Nothing known in physics can support the core against its own gravity. The collapse continues, compressing matter to infinite density at a point called a singularity, surrounded by an event horizon from which nothing can escape. The stellar remnant becomes a black hole. The supernova explosion might proceed normally, leaving a black hole at the center of the expanding debris. Or if the core is sufficiently massive, the collapse might be so catastrophic that it swallows the infalling material before an explosion can develop, creating a black hole with little or no visible supernova, a so-called failed supernova. Stellar mass black holes created from supernova typically contain 5 to perhaps 20 solar masses. They're invisible except through their gravitational effects and the radiation from material falling into them. In X-ray binary systems, black holes reveal themselves through the extremely energetic X-rays emitted by infalling material, distinguishable from neutron star systems by the absence of pulsations and by the inferred mass. Anything above 3 solar masses cannot be a neutron star and must be a black hole. Some supernova types leave nothing behind at all. Pair instability supernova occur in extremely massive stars, those with initial masses exceeding about 130 solar masses. In the cores of these giants, temperatures and photon energies become so extreme that gamma-ray photons spontaneously convert into electron-positron pairs. This pair production removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is obliterated. No neutron star, no black hole, just an expanding cloud of debris. These explosions were more common in the early universe, when stars could grow more massive due to lower metallicity, but they might still occur in regions with primordial composition. The observable supernova remnant, the expanding shell of gas and dust, evolves over thousands to tens of thousands of years. Initially, the blast wave plows through the surrounding interstellar medium at thousands of kilometers per second, creating a hot, shock-heated region. The Crab Nebula, the remnant of the 1054 supernova, is still expanding at about 1,500 kilometers per second. The pulsar at its center powers the nebula's glow, creating a wind of relativistic particles that illuminate the expanding gas. Older supernova remnants like the Cygnus Loop, about 10,000 years old, have expanded to hundreds of light years across. The blast wave has slowed to tens of kilometers per second, and the shock is transitioning from adiabatic expansion, where the remnant retains its heat, to radiative expansion, where the shocked gas cools and radiates energy away, creating the delicate filaments visible in optical and X-ray images. Eventually, after perhaps 100,000 years, the remnant merges with the surrounding interstellar medium, its expansion slowing to match the general motion of gas in the galaxy. The enriched material, oxygen, carbon, silicon, iron, and other elements forged in the star and the explosion, mixes into interstellar clouds. These enriched clouds eventually collapse to form new generations of stars and planets, incorporating the elements created by the previous stellar generation. Every atom of oxygen you breathe, every atom of carbon in your body, was created in a star and dispersed by a supernova, later incorporated into the molecular cloud from which the Sun and Earth formed. What's left after a star explodes depends on the fine details of mass, composition, rotation, and magnetic fields, whether the core becomes a neutron star or black hole, whether the neutron star becomes an observable pulsar or remains radio quiet, whether the magnetic field is ordinary or reaches magnetar strength. Each stellar death creates a unique remnant, a compact object encoding in its properties the history of the parent star and the violence of its death, objects that will persist for trillions of years after the last stars have formed, cooling slowly in the expanding universe, monuments to stellar death that simultaneously mark endings and beginnings in the grand cycle of cosmic recycling. Where baby stars come from. Stars are not born in the bright, empty spaces between galaxies or in the clear voids of interstellar space. They emerge from darkness, from vast clouds of gas and dust that hang in the spiral arms of galaxies, regions so dense with obscuring material that they appear as black patches against the glowing background of the Milky Way. These stellar nurseries, called molecular clouds, are the cosmic wombs where stars begin their lives, places where gravity, temperature, pressure, and chemistry conspire to transform diffuse gas into brilliant spheres of nuclear fusion that will shine for millions or billions of years. The process begins with a molecular cloud, an enormous accumulation of gas and dust drifting through the galaxy. These clouds are cold, typically only 10 to 20 degrees above absolute zero, and they're composed primarily of molecular hydrogen, two hydrogen atoms bonded together, mixed with helium and trace amounts of heavier elements. The clouds also contain dust grains, tiny particles of silicates and carbon compounds, each grain smaller than a bacterium, but collectively making up about 1% of the cloud's mass. These dust grains play a crucial role despite their small mass contribution, shielding the interior of the cloud from starlight and cosmic rays, allowing it to remain cold enough for molecules to survive. Molecular clouds range in size from relatively small clouds, a few light years across, to giant molecular cloud complexes spanning hundreds of light years and containing enough material to form hundreds of thousands of stars. The Orion Molecular Cloud Complex, one of the nearest star-forming regions at about 1,300 light-years from Earth, contains enough gas to make roughly 100,000 stars, like the Sun. The cloud extends across much of the constellation Orion, with the famous Orion Nebula marking just one small region where star formation is particularly active and visible. For stars to form, something must disturb these clouds, compressing them beyond a critical threshold where gravity overwhelms the internal pressure that normally keeps the cloud stable. This compression can come from several sources. A shockwave from a supernova explosion, travelling through space at thousands of kilometers per second, can slam into a molecular cloud and compress it. The spiral density waves that create the spiral arms of galaxies compress gas as it enters these regions, triggering star formation that lights up the spiral arms with young, bright stars. Even the radiation and stellar winds from existing massive stars can compress surrounding gas, triggering new generations of star formation in a process that propagates through the cloud. Once a region of the cloud is compressed, gravity takes control. The denser parts of the cloud pull in surrounding material, growing denser still. This runaway process would cause the entire cloud to collapse into one enormous star, but molecular clouds are turbulent places, filled with eddies and currents of gas flowing in different directions. This turbulence, combined with the cloud's rotation and magnetic fields threading through it, breaks the cloud into fragments. Each fragment, typically containing anywhere from a fraction of a solar mass to tens of solar masses, becomes the seed of a star or a small system of stars. As a fragment collapses, it heats up. This might seem counterintuitive. How does something heat up as it collapses in the cold of space? The answer lies in gravitational potential energy. As gas falls inward, it accelerates, gaining kinetic energy. When fast-moving atoms and molecules collide with other particles, they convert their kinetic energy into thermal energy, heat. The center of the collapsing fragment grows hotter and denser, while the outer regions continue to fall inward, feeding the growing concentration at the center. The collapse doesn't proceed smoothly or uniformly. The fragment rotates, inherited from the overall rotation of the molecular cloud, and conservation of angular momentum means it spins faster as it shrinks, just as an ice skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the center. Instead, material settles into a rotating disk around the growing protostar, the nascent star at the center. This disk, called a protoplanetary disk or protostellar disk, channels material toward the protostar, while the outer parts remain in orbit, eventually becoming the raw material from which planets might form. The young protostar, deeply embedded in the infalling gas and dust, is invisible at optical wavelengths. The surrounding cocoon of material absorbs any visible light the protostar emits and re-radiates it as infrared radiation. This is why infrared telescopes are essential for studying star formation. They can penetrate the dust and observe the protostars hidden within molecular clouds. The Spitzer Space Telescope and now the James Webb Space Telescope have revealed thousands of these embedded protostars, showing snapshots of stars at various stages of formation. As the protostar continues to accrete mass, its central temperature and pressure climb steadily. The journey from cold molecular gas to a hot protostar takes roughly 100,000 years for a Sun-like star, though this timescale varies depending on the protostar's mass. More massive protostars collapse more quickly because their stronger gravity accelerates the infall. Less massive protostars take longer, sometimes millions of years, to fully form. The protostar doesn't simply accrete all the material that falls towards it. Young protostars are violent, magnetically active objects. Magnetic field lines threading through the protostar, and its disk can become twisted and tangled by the rotation. And these magnetic fields launch jets, narrow beams of gas that shoot outward from the protostar's poles at speeds of hundreds of kilometers per second. These jets are one of the most distinctive signs of active star formation. The Hubble Space Telescope has captured stunning images of these jets, often light years long, streaming away from young stars still hidden within their dusty cocoons. The jets serve an important function. They carry away angular momentum and energy that would otherwise prevent further accretion. Without some mechanism to remove angular momentum, the disk would simply spin faster and faster, and material would stop falling onto the protostar. The jets, along with stellar winds, outflows of gas from the protostar's surface, solve this problem, allowing the protostar to continue growing even as it spins. Where the jets slam into the surrounding molecular cloud, they create glowing knots and filaments called Herbig-Haro objects, named after astronomers George Herbig and Guillermo Haro, who studied them in the 1950s. These objects glow because the jet's high-speed collision with the ambient gas heats it to thousands of degrees, causing atoms to emit light. Herbig-Haro objects can move visibly over timescales of years, and they serve as signposts marking regions of active star formation. The accretion phase lasts for roughly 1 million years, though again this varies with stellar mass. During this time, the protostar is not yet a true star because no nuclear fusion occurs in its core. It shines from gravitational energy. The energy released as material falls onto its surface, and as it slowly contracts under its own weight. This contraction, described by Hermann von Helmholtz and Lord Kelvin in the 19th century, heats the interior gradually. Eventually, after millions of years of contraction and heating, the core temperature reaches approximately 10 million degrees Celsius. At this critical temperature, protons moving at extremely high speeds collide with enough energy to overcome their mutual electrical repulsion and fuse together, creating helium and releasing energy. This ignition of hydrogen fusion marks the birth of a true star. The protostar becomes a main sequence star, entering a stable phase where the energy released by fusion creates outward pressure that balances gravity's inward pull. For a star like the Sun, this moment arrives roughly 10 million years after the initial collapse began. The newly formed star is now generating its own energy through nuclear reactions rather than relying on gravitational contraction. It will remain on the main sequence, fusing hydrogen in its core for about 10 billion years, 100 times longer than it took to form. Not all fragments in a molecular cloud form single stars. Many form binary or multiple star systems where two or more stars orbit each other. The fragmentation process can produce two separate cores within a single disk, each growing into a star. Or a protostellar disk can become gravitationally unstable and fragment, forming additional stars. About half of all stars exist in binary or multiple systems, making our single sun somewhat unusual. The smallest fragments don't have enough mass to ever ignite hydrogen fusion. Objects below, about 0.08 solar masses, roughly 80 times Jupiter's mass, never reach core temperatures high enough for hydrogen fusion. These failed stars, called brown dwarfs, glow dimly from their residual heat and from the fusion of deuterium, a heavy isotope of hydrogen that fuses at lower temperatures than normal hydrogen. Brown dwarfs slowly cool over billions of years, gradually fading from view. The most massive fragments form massive stars, objects with tens of times the Sun's mass. These stars form quickly, sometimes in just a few 100,000 years, and burn brilliantly but briefly. They produce intense ultraviolet radiation that ionizes the surrounding gas, creating glowing H2 regions like the Orion Nebula. The radiation pressure from these massive stars is so strong that it can halt further star formation nearby, blowing away the remaining gas and effectively shutting down the stellar nursery. The wind and radiation from massive young stars create expanding bubbles in the molecular cloud, clearing out regions and compressing gas at the bubble's edges. This compression can trigger new star formation, creating generations of stars with the oldest stars at the center and progressively younger stars toward the periphery. The entire process is self-propagating until the molecular cloud is either dispersed entirely or exhausted of dense gas. When the most massive stars explode as supernovae after just a few million years, they inject tremendous energy into their surroundings, heating and dispersing the remaining molecular cloud and enriching it with heavy elements created in the star and in the explosion. The shockwave from the supernova can compress nearby clouds, triggering new rounds of star formation. In this way, star formation is a cyclical process. Stars form from clouds, massive stars disrupt clouds, supernova shockwaves compress new clouds, and stars form again. The entire life cycle from molecular cloud to dispersed star cluster takes roughly 10 to 20 million years. The Orion Nebula, one of the most famous star-forming regions visible to the naked eye, contains stars that are only about 1 to 2 million years old, cosmic newborns still surrounded by the glowing remnants of the cloud that birthed them. Over the next few million years, the radiation from these young stars will disperse the remaining gas, leaving behind a star cluster that will gradually spread apart as its members drift through the galaxy. Understanding where baby stars come from means understanding one of the fundamental cycles of the cosmos. The gas from which stars form was once inside previous generations of stars. Those stars fused hydrogen into helium, helium into carbon and oxygen, and heavier elements still, then returned that enriched material to space through stellar winds and supernova explosions. That material mixed into molecular clouds and became incorporated into new stars, including our Sun, which formed about 4.6 billion years ago from a molecular cloud that contained the ashes of earlier stellar generations. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stars that formed, lived, died, and seeded the molecular cloud from which the Sun and Earth eventually emerged, continuing the ancient cycle of stellar birth and death that has shaped the galaxy since stars first began forming over 13 billion years ago. What is dark matter and why can't we see it? Imagine trying to understand a conversation in a crowded room while wearing earplugs. You can see people's mouths moving, see their gestures, watch them react to each other, but you can't hear the words being spoken. You know communication is happening. The evidence is clear in the movements and responses, but the medium of that communication remains completely inaccessible to you. This is somewhat like humanity's relationship with dark matter. We can see its effects throughout the universe, observe how it shapes galaxies and bends light, measure its gravitational influence on everything around it. Yet the substance itself remains invisible and intangible to every instrument we've built to observe the cosmos. Dark matter makes up approximately 85% of all matter in the universe. Let that sink in for a moment. Everything you can see, every star, every galaxy, every glowing nebula, every planet, every atom in your body represents only about 15% of the matter that exists. The rest, the overwhelming majority, is dark matter, and it surrounds us, permeates us, flows through us, yet reveals itself only through its gravitational effects. The story of dark matter's discovery begins not with a sudden revelation, but with decades of observations that didn't quite make sense. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving within the cluster and used these velocities to calculate how much mass must be present to keep the cluster gravitationally bound. What he found was shocking. The galaxies were moving so fast that they should have escaped the cluster's gravity and flown apart long ago, unless the cluster contained far more mass than could be seen in the form of stars and gas. Zwicky proposed that some form of dark matter must exist, matter that didn't emit light, but provided the additional gravity needed to hold the cluster together. His idea was largely ignored for decades. It seemed too radical, too strange. Surely there was a simpler explanation. Perhaps astronomers were just missing some normal matter, dust clouds or dim stars that hadn't been detected yet. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin conducted detailed studies of how stars and gas move within spiral galaxies. According to the laws of gravity and orbital mechanics, objects farther from the center of a galaxy should move more slowly, just as planets farther from the Sun orbit more slowly than those closer in. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 years to complete one orbit. The same principle should apply to galaxies. Stars near the edge should crawl along in their orbits compared to stars closer to the galactic center. But that's not what Rubin found. She observed that stars at the outer edges of galaxies move just as fast as stars closer to the center, sometimes even faster. The rotation curves of galaxies were flat rather than declining, which could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars and gas. And this extra mass wasn't concentrated at the center where most of the visible matter was. It extended far beyond the visible disk, forming a massive spherical halo of invisible matter surrounding each galaxy. Picture a galaxy in your mind, a spiral with graceful arms of stars spinning around a bright central bulge. Now imagine that entire visible structure is embedded within a much larger sphere of dark matter, extending perhaps 10 times farther than the visible stars reach. This dark matter halo contains several times more mass than all the stars, gas and dust combined, yet it emits no light, no radio waves, no X-rays, nothing we can detect directly. The evidence for dark matter extends far beyond galaxy rotation curves. Gravitational lensing provides some of the most compelling proof. According to Einstein's theory of general relativity, mass warps the fabric of spacetime, and light follows the curves in this warped spacetime. When light from a distant galaxy passes near a massive object, its path bends. Just as light bends when passing through a glass lens. The amount of bending depends on how much mass is present. Astronomers observe light from distant galaxies being bent and distorted as it passes through galaxy clusters. By measuring this distortion carefully, they can map out exactly where mass is concentrated in these clusters, creating what's essentially a gravity map. When they do this, they find that most of the mass, about 90%, isn't where the visible galaxies are. It's distributed in a much larger structure, consistent with massive halos of dark matter. One of the most dramatic examples came from studying a structure called the Bullet Cluster, where two galaxy clusters had collided and passed through each other. During the collision, the hot gas from each cluster, which is normal matter, slowed down and remained near the collision site, heated by the impact. But the dark matter from each cluster, which doesn't interact with normal matter except through gravity, passed right through and continued moving. By mapping the gravity through gravitational lensing, astronomers could see that most of the mass had separated from the visible gas, providing direct evidence that dark matter and normal matter are distinct substances. So what is dark matter made of? This is one of the deepest mysteries in physics. And the honest answer is that we don't know. We know what it isn't. It's not made of atoms, protons, neutrons, or electrons. It's not any form of normal matter that we're familiar with. We call normal matter baryonic matter. And dark matter is something entirely different, something that exists outside the catalogue of particles that make up everything we can touch and see. The most popular hypothesis is that dark matter consists of particles that simply don't interact with electromagnetic radiation. Light, radio waves, X-rays, any form of light across the entire spectrum. These hypothetical particles, often called WIMPs, weakly interacting massive particles, would have mass and exert gravity, but they wouldn't emit, absorb, or reflect light. They would be essentially transparent to electromagnetic radiation, which is why we can't see them. Imagine a particle that could pass through matter almost as if it weren't there. Billions of these particles might be flowing through your body right now, passing through the Earth, streaming through space, and you would never know. They don't collide with atoms, don't scatter off electrons, don't leave any trace except for their collective gravitational influence. This is what dark matter particles would be like. Ghost particles that fill the universe, but interact with normal matter only through the weakest of forces. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and background radiation, trying to catch the rare interaction of a dark matter particle with normal matter. These detectors contain tanks of specially purified materials, cooled to near absolute zero, instrumented with sensors that can detect the tiniest energy deposit. The idea is that occasionally, very rarely, a dark matter particle might collide with a nucleus in the detector, releasing a tiny amount of energy that could be measured. So far, despite decades of searching with increasingly sensitive experiments, no one has definitively detected a dark matter particle. Another possibility is that dark matter consists of primordial black holes that formed in the early universe, not from collapsing stars, but from density fluctuations shortly after the Big Bang. These would be dark by their very nature, since black holes don't emit light. However, careful observations suggest that primordial black holes can't account for all the dark matter. They would produce observable effects, like gravitational microlensing when they pass in front of distant stars, and we don't see these effects at the level that would be expected if most dark matter were in this form. Some theories propose that dark matter might be axions, extremely light particles that were produced in enormous quantities in the early universe. These would be very different from WIMPs, much lighter, much more numerous, behaving more like a wave than individual particles. Detecting axions requires different experimental approaches, and several experiments are currently searching for these elusive particles. There's even a possibility, though most physicists consider it less likely, that dark matter doesn't exist at all. Instead, perhaps our understanding of gravity is incomplete, and the theory needs to be modified to explain the observations without requiring invisible matter. These modified gravity theories, called MOND, modified Newtonian dynamics, and various relativistic extensions, can explain some observations but struggle with others, like the bullet cluster, which seems to require actual dark matter to explain. Dark matter played a crucial role in the formation of structure in the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. These variations were the seeds of all future structure: galaxies, galaxy clusters, and the cosmic web. But normal matter coupled to radiation in the early universe couldn't collapse and clump together efficiently. Dark matter, which didn't interact with radiation, could begin collapsing earlier, forming gravitational wells that normal matter eventually fell into. Without dark matter, galaxies as we know them couldn't have formed in the time available since the Big Bang. Today, dark matter continues to shape the universe. It forms the gravitational scaffolding along which galaxies are distributed. It determines how galaxy clusters form and evolve. It affects how galaxies merge and interact. Every large-scale structure in the universe exists because of dark matter's gravitational influence. On smaller scales, dark matter fills our own galaxy. The Milky Way sits within a dark matter halo that extends far beyond the visible disk of stars. This halo contains perhaps 10 times more mass than all the stars in the galaxy. As our solar system orbits the galactic center, we're moving through this sea of dark matter. At any given moment, thousands of dark matter particles might be passing through every cubic centimetre of space, though detecting even one of them remains beyond our current capabilities. The invisibility of dark matter is not a limitation of our instruments, it's a fundamental property of the substance itself. We can't see it because it doesn't interact with light in any way. We can't build a better telescope or a more sensitive camera to observe it directly. The only way we know it exists is through its gravitational effects on the things we can see. It reveals itself in the motion of stars, the bending of light, the structure of the cosmic web, and the evolution of the universe itself. Dark matter surrounds us, shapes the cosmos, and yet remains one of the deepest mysteries in science, a reminder that the universe is far stranger and more complex than our everyday experience might suggest. What happens at the edge of a black hole? At the edge of a black hole lies one of the most extreme boundaries in the universe, a point of no return called the event horizon. This invisible surface marks the place where gravity becomes so overwhelmingly powerful that nothing, not even light itself, can escape. Cross this threshold, and you are severed from the rest of the universe forever, drawn inexorably toward the singularity at the centre. Understanding what happens at this edge requires thinking about space and time in ways that challenge everything. Our everyday experience tells us about how reality works. Imagine approaching a black hole from a safe distance. At first, it wouldn't look like much, just a region of absolute darkness against the star-filled background of space. But as you drew closer, you would begin to notice something strange happening to the light around you. Stars behind the black hole would appear distorted, their light bent around the black hole's mass in graceful arcs. Some stars would appear in multiple locations simultaneously as their light took different curved paths around the black hole to reach your eyes. This gravitational lensing creates a visual effect, like looking through a cosmic funhouse mirror, with the entire background of space warped and twisted around the dark sphere. The event horizon itself is defined by a specific radius from the center of the black hole, called the Schwarzschild radius. For a black hole with the mass of our Sun, this radius would be about 3 kilometers. For a supermassive black hole, like the one at the center of our galaxy, which contains about 4 million times the Sun's mass, the event horizon stretches millions of kilometers across. The radius grows linearly, with mass double the mass and you double the radius. Despite these varying sizes, the fundamental nature of the event horizon remains the same. It's the mathematical surface where the escape velocity equals the speed of light. Think about what escape velocity means. On Earth, you need to throw something upward at about 25,000 miles per hour for it to escape the planet's gravity and never fall back down. Get closer to a massive object and the escape velocity increases. At the event horizon of a black hole, the escape velocity reaches 186,282 miles per second. The speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever escape. But here's where things become truly strange. Time itself behaves differently near a black hole's edge. According to Einstein's general relativity, gravity doesn't just bend space, it warps time as well. The stronger the gravity, the slower time passes relative to an observer far away from the gravitational source. Near the event horizon, this time dilation becomes extreme. Picture two observers, one hovering safely far from the black hole, another descending toward the event horizon. The descending observer checks their watch, and everything seems normal to them. Time passes at its usual rate from their perspective. They breathe normally, their heart beats regularly, they think their thoughts at the normal pace. But to the distant observer watching through a powerful telescope, something bizarre is happening. The descending person appears to be moving slower and slower. Their movements become sluggish, their signals take longer and longer to arrive, and as they approach the event horizon, they appear to nearly freeze in place. This isn't an optical illusion or a trick of perception. Time genuinely runs slower in stronger gravitational fields. As the descending observer approaches the event horizon, each second they experience corresponds to longer and longer periods for the distant observer. At the exact moment they cross the event horizon, from the distant observer's perspective, time for them appears to stop completely. They would appear frozen at the edge, never quite crossing over, their image becoming increasingly redshifted and dim, eventually fading from view entirely. But from the perspective of the person crossing the event horizon, nothing special happens at that precise moment. There's no wall, no barrier, no sensation of crossing a threshold. They would pass through the event horizon and continue falling inward, still experiencing time normally from their own reference frame. This is one of the most counterintuitive aspects of black holes. The event horizon is only special to outside observers. To someone crossing it, the moment passes without any local indication that anything significant has occurred. However, there is something that would become increasingly noticeable as you approached and crossed the event horizon: tidal forces. These arise because gravity weakens with distance, and different parts of your body would be at different distances from the black hole's center. If you fell feet first toward the black hole, your feet would experience stronger gravity than your head. This difference in gravitational pull creates a stretching force. For a stellar mass black hole, these tidal forces become extreme well before you reach the event horizon. The difference in gravitational pull between your head and feet would stretch you vertically while simultaneously squeezing you horizontally, a process astrophysicists have termed spaghettification. Long before reaching the event horizon, the tidal forces would overcome the molecular bonds holding your body together, stretching you into a thin stream of atoms. This would be an absolutely fatal experience occurring far from the event horizon itself. For supermassive black holes, the situation is different. Because they're so much larger, the tidal forces at the event horizon are actually quite mild. You could cross the event horizon of a supermassive black hole, and for a while at least, experience no unusual forces at all. The spaghettification would come later, as you continued falling inward toward the singularity where tidal forces eventually become infinite, regardless of the black hole's size. The event horizon is also where the nature of space and time exchange roles, in a sense. Outside the event horizon, you can choose your direction in space. You can go left or right, up or down, toward or away from the black hole. Time, on the other hand, only flows in one direction, forward. But once you cross the event horizon, this changes. Moving inward toward the singularity becomes as inevitable as moving forward in time is outside the black hole. Just as you can't choose to move backward in time in normal space, you can't choose to move away from the singularity once inside the event horizon. All possible paths through space-time, every trajectory you could take, lead inward. Light behaves strangely at the event horizon as well. Just outside the horizon exists a region called the photon sphere, where light can orbit the black hole in unstable circular paths. Photons at exactly this radius, moving in exactly the right direction, will circle the black hole indefinitely, though any tiny perturbation will cause them to either spiral inward or escape outward. If you could somehow position yourself at the photon sphere and look sideways, you might theoretically see the back of your own head as light from you travelled around the black hole and returned. At the event horizon itself, photons can move along the surface, neither escaping nor falling inward, but this is an unstable equilibrium. Any photon aimed even slightly inward will fall toward the singularity. Any photon aimed even fractionally outward will escape to infinity, though heavily redshifted by the time it reaches distant observers. The effects of gravitational redshift become extreme near the event horizon. Light climbing out of a deep gravitational well loses energy, shifting toward longer wavelengths, toward the red end of the spectrum and beyond into infrared and radio waves. A flashlight shining from near the event horizon would appear dimmer and redder to a distant observer. Right at the event horizon, light is redshifted infinitely, meaning the energy of any photon trying to escape becomes zero. This is another way of understanding why nothing can escape. Even light, trying to leave the event horizon, has all its energy drained away by the gravitational field. Black holes can rotate, and rotation adds another layer of complexity to the event horizon. A rotating black hole drags space-time around with it in a process called frame dragging. Close to the black hole, space itself is being pulled around in the direction of rotation. There's a region called the ergosphere outside the event horizon, where this frame dragging is so strong that nothing can remain stationary. Everything must rotate with the black hole, even if it has enough energy to eventually escape. For a rotating black hole, the event horizon is actually smaller than it would be for a non-rotating black hole of the same mass, and it's oblate rather than perfectly spherical, bulging slightly at the equator. At the poles, you could get closer to the singularity before crossing the point of no return than you could at the equator. The material falling into a black hole doesn't simply disappear the moment it crosses the event horizon. Before crossing, matter often forms an accretion disk, a swirling disk of gas, dust and plasma spiraling inward. Friction in this disk heats the material to tremendous temperatures, often millions of degrees, causing it to radiate intense X-rays and other radiation. This radiation comes from outside the event horizon and can escape, making accreting black holes among the brightest objects in the universe, even though the black hole itself emits nothing. As material in the accretion disk spirals closer to the event horizon, it accelerates to tremendous velocities, often reaching significant fractions of the speed of light. The innermost stable circular orbit, the closest distance where material can orbit without inevitably falling in, lies just outside the event horizon. Material at this radius whips around the black hole in fractions of a second, subjected to intense tidal forces and heated to extreme temperatures before making its final plunge across the event horizon. At the quantum level, something remarkable happens right at the event horizon. Stephen Hawking predicted that quantum effects near the event horizon would cause black holes to emit radiation, now called Hawking radiation. Virtual particle pairs constantly pop into existence throughout space, normally annihilating each other almost immediately. But at the event horizon, one particle of the pair can fall into the black hole, while the other escapes. To a distant observer, the black hole appears to be emitting radiation with a temperature inversely proportional to its mass. For stellar mass black holes, this temperature is incredibly tiny, far colder than the cosmic microwave background, so the effect is purely theoretical at present. But over unimaginably long timescales, Hawking radiation would cause black holes to slowly evaporate. The event horizon represents one of the most profound boundaries in physics, a one-way membrane in space-time itself. It's a place where our intuitions about time, space, and causality break down, where the fabric of reality becomes so warped that the normal rules no longer apply. Everything that crosses this boundary is lost to the outside universe forever, adding to the black hole's mass and slightly expanding its event horizon, while the information about what fell in appears to be lost forever, creating paradoxes that physicists still struggle to resolve. The edge of a black hole is truly an edge, not just of a physical object, but of our ability to observe, to know, and to understand the universe.